So stat E. (8.1.1) sampling distribution of sample proportions. Day 1. And again, a lot of what we are learning is going to be off the video in regards to what we're doing within the Desmos. Now, first and foremost, I need to make sure you understand the difference between a population versus a sample. We've talked a lot about this throughout our unit, our course. Sorry, not our unit. So in a population, this is everyone of interest in the population. We often call this, when we conduct this, we call this a census. Okay? So if we were able to ask every single student and when I talk about certain things like MCAS scores for BCLA, for RBA, well, we have everybody's MCAS scores. We have the data of everybody. I can look at your rosters and look at everybody's MCAS scores, how you did in the 10th grade. I have that. There's no need for statistics, inferential statistics, because we have everybody. We have the full population. But however, if I'm asking how does the school do and how does the history, how are we going to do in the future of RBA, I can use your data as a sample. And so a sample, again, just as a reminder, is a portion of the population. Now, ideally, we want a random, unbiased. We want it to be unbiased. And, yeah, so we want, let me just do it this way. We want it to be random and therefore unbiased. So that's who we're asking. Who are we interested in? If we're interested in, again, if I'm interested in students at RBA, that's the population. If I use you as a sample, or if I use you and I ask you, you would be the sample. You are a portion of all of the population. One of the first things we covered on the first day. Now, the next thing we're going to talk about, though, is what is known as the parameter. And the parameter is the variable we want to know about from the population. You'll often hear this say the population parameter. What is it that we want to know? So in the problem that what we want to know, for example, in the population, in the do now that we've been doing, the population are those migrants, all right? The migrants in the caravan coming from Central America. That's the population. What does everybody look like? All right? Well, not everybody, sorry. Who is everybody? Everybody is all those migrants. Every single one of them. We can't talk to, we can't interview, we can't see every single one. What we can do is we can look and we take a sample, and therefore we look at what's called a statistic. And a statistic is the estimate of the population parameter from the sample. So oftentimes you'll hear me say the sample statistic. The statistic comes from a sample. The parameter is the population. So population is to sample as parameter is to statistic. And the statistic is an estimate of the parameter. So in this problem, the parameter, what are we interested in? We're interested in what is the true percentage. What percentage of migrants are male? That's what we're interested in. Okay? That's the kind of the question. The statistic is, of those that we sampled, what percentage of those sampled, of the migrants sampled, are male? Now, in 8.1, in our lesson for 8.1, our parameter is going to be known as P, lowercase p, which stands for the proportion of the population. I'm going to actually underscore this one. The proportion of the population who are successes. Now, the reason why I have the population as success is because for every problem, it's going to change. So in this problem, again, so our parameter in the do now, the problem that we're trying to build up is we want to find what is the proportion, the percent. Remember, percentage and proportion are the same thing. Just one is written as a decimal versus a percentage sign. So we're looking at the percentage, the proportion of the migrants who are male, or adult males, mostly is what we're looking for. Because that's what's the big question. So what does the male outlook look like? So just as remember, a percentage is a proportion. I.e., an example, 81% is 0.81. The statistic, though, we're in statistics. So the statistic for the parameter P is known as P hat. Literally, we read this as P hat. That's how we read it. So when you say this verbally, it's P hat, but it's also known as the sample proportion. The sample proportion. That's our notation for the sample proportion. The proportion of the sample who were blank successes. Now, I do want to know, I did something very minor here that as a true statistician, I want you to know the difference of. Notice the difference of tense I used, and I did it very subtly. When talking about the population, I want to know what the population looks like. What is it? What is the population parameter? What does it look like? So I'm saying I use that R. I'm using current, present tense. Because I don't know what it is. All right? Versus when I talk about the sample, I talk about the sample in past tense. And the reason why I'm using the sample in past tense is because I know what the sample already is. I collected the sample, and this is what it was, not what it is. Are versus were. Are is, was, were. P hat can be calculated as X, the number of successes, over N. Now remember, in our previous unit, a binomial, we did X, we studied X, the binomial distribution, and N is the number of success or sample size. So, for example, we're going to do an example very closely. If x is, let me just do an example, i.e., if x is 300 and n is 500, then p hat would be 300 over 500, which would be 0.6. That's how we kind of write it down. So taking this information right here, I'm going to open up your next slide. Using the next slide, can you tell me and match it up? And sorry, it will not tell you if it's correct and wrong. I had to recode it and I didn't recode it. I spent a lot of time. I spent, I don't know, like 5 hours maybe, really trying to put together the next 6 days of lessons and how it would go and which slides worked best with which. And I was pulling from many different locations. I tried to create a little bit of my own. I tried to reuse some stuff that I had in the past. I started to reuse some stuff that was new like this. And so I did not go back in and check the coding of saying that if it tells you that it's correct or not. So some of this stuff will not say you are correct. It's about doing it. So, but I can see it on my side. So which ones, so I already see, for example, Amanda, yep, nailed all the card sorts right away. So can you match these into, it says 3 groups. That is a typo. It says actually should be saying 2 groups. And going into it. So let's take a look at here. Students right here. Which go together. One of the very first major things we want to understand is which vocabulary should go together. Vocabulary is a big thing. Good, Naima. Just nail those. Oh, you had it. Just put the others together. Huh? Oh, okay. I was like, you had it. Yes. So the population, the parameter is the population proportion, which is the letter P, and the sample proportion, the statistic that we are studying is the sample proportion, which is P hat. So on Friday, the statistic is going to change. So we're going to have a parameter, and on Friday, our parameter will be the population mean, and then our statistic will be the sample mean. And so we'll have mu, right, the mean, and we'll have x bar, sample mean. All right, so in this problem, going on to slide 9 now. So here was one of the information. So this was a data that we had gotten. Immigrant Citizen Survey conducted a random sample of this database, surveying recent immigrants to Spain who were 15 and older. 257 of 583 immigrants sampled were male. So this is an example of how something is. And what we're just doing right now is just seeing how investigative statistics actually works. So my question to you, based on this final paragraph right here, who is the population? What is the parameter of interest? Who were in the sample? What was the sample? And what was the statistic that was found? Can you find these 4 pieces of information? These 4 pieces of information are important. We'll give you 2 minutes to attempt it, and then I'll go over it. I get these junk messages so much, like 4 a day these days. Jeez. So who is the population? What was the parameter? The population is verbal. The only thing that's going to be technically a number will be the statistic. And part of the sample. So let me show you. So the population in this problem, the population is immigrants to Spain 15 and or older. That's Spain. Spain, people, Spain. Immigrants. Immigrants to Spain 15 and older. That's who the population was from. It's every immigrant, all immigrants. So basically, it's all immigrants to Spain who are 15 and older. Okay, that's the population. What am I interested? I am interested in the proportion or percentage, the proportion of immigrants to Spain, 15 plus, who are what? I'm interested in that who are what? No, that's the part of the population. I'm not interested in that. That's who they are. Male. Who are male? Because what's the binary part? What is the binary thing? It's either they're male or they're male, right? They're male or female. That's it. Everybody is an immigrant from Spain who's 15 or older. That's everybody. But what checks them off of being yes and no? Success and failure. They're male or female. The sample. Who is the sample? How many? 583 immigrants. So what is my statistic? 257 divided by 583. Which when I plug that into my calculator, I get 0.441. Which is also known as about 41.1%. But 0.441 is my statistic. So in my sample statistic is that I found as my statistic that 41.1% of the migrants were male. Now remember, what was the claim? What did they, in the beginning of this in the beginning of this work, what was the claim by the EU and Trump? What percentage did they claim were male? 60%. Okay? So this is how statistics works in its most infant stage. And it's still kind of wrong, but it's okay. You'll kind of get it right. 60%. The claim is 60% are male, 60% or more. We took a sample, and in our sample, we got 41%. Now, I hope you understand that 41% is, and this is what we did early in the school year. 41% is a lot smaller than 60%. Do you agree? That is significantly lower. It's obviously, which means significantly lower than 60%. So what we would say, and this is what we did, by the naked eye, I can see that 41% is much, much, much lower than 60%. So that would be statistically significant. I would say that is unusually low. If it was indeed 60%, I have an argument here. Now, what we're going to do, though, is what happens, how can I answer that more concretely? Where's the math behind it then it looks small? Because what somebody sees as a small difference, another person might not see as a small difference. And that's what we're going to do. And so we're going to have a little investigative thing. So please, to show me that you understood what we did, please match up on the slide 10, which is just to show me what we just did, putting it in as the matching. You should have 4 groups on this one. So please match these. Did you... You're missing. No, you got ones off. A couple. Ricky, you got it.
You said no?
You're missing. You 2 of them are off. 2 of them are correct. 2 of them are wrong. Natalie, good job. Good job. Let me see which one you got off. Your population and parameter are backwards. The population is all 15-year-olds. The parameter is the proportion of migrants that are male. All right, so we're going to do a little activity now. So here is how it's kind of going to work. So to show you how statistics actually works in a smaller scale, so we're not talking about those big numbers, that 257 out of 583 and all that. We're not going to look at that number right now. Let's simple it down much smaller. First off, please click the link right there. Please click this link, one categorical variable, single group, so that you can follow along and do what's going on. So let's say that the entire caravan was 18 males and 12 females. Okay? So there are 60% are males, which is 18, and 12 are females. Think of this as the same thing as the marbles that go in the bag, right? There's the marbles that are in there. So 18 of those marbles are represented as males. They could be like blue, and 12 of the marbles that are inside the bag represent females, non-males. They can be yellow, green, whatever other different color there is. Now, we're gonna type this in right here. So you should follow along as it goes along, because you're gonna take a screenshot and you're gonna upload it to get full credit. And I'll show you what that looks like. So we're clicking the link, everybody, so that you can get a little practice here. So our variable here, as was shown over here, is male immigrants. We have male that are 18 males, and we have female, which is 12 females. Okay, we're going to click Begin Analysis. Now, I don't care about this part right here. This is all that kind of stuff we played around with early in our course. We're now going to go down to the bottom, and we're going to do this inference right here. This is going to help us see what happens. And what we're going to do basically is we're going to take a random sample. So we're going to take a sample of males from this. And the question is, how many males is there? So we'll take a sample. The hypothesized value is 60%. So we're going to put 60 right there. And we're going to add one sample at a time. And so here's what's going to happen. Basically, this is what's going on behind here. This is with replacement. So basically what's happening is the computer is going to randomly select a person, or a marble from the bag. Okay? They're going to select 30 marbles from the bag. They're going to select one, put it back in, shake it up. Select one, put it back, shake it up, put it back in. They're going to do this every single time. They're going to shake, put it in, back, shake, put it in, shake, shake it back. So every single time they select a marble or select a migrant, there is a 60% chance that they are male. Does everybody get that? Every single time there's a 60% chance of being a male. And every single time there's a 40% chance of it being a female. And so what the marbles are going to do is it's going to select 30 marbles. It's going to select 30 marbles, okay? Now, on average, how many of those marbles should be males? How many males should be selected? 18. On average, 18 of them should be male. Are we going to get 18 males every time? No. Sometimes we'll get a little bit more. Sometimes we'll get a little bit less. Sometimes we might get really unlucky, right? We might get 12 males. We might get 25 males. Okay? Our parameter is 60%, 0.6. So when I hit add sample, boom. What has happened here, what again? So what this is saying is that the computer took a sample of 30 and it got 17 males. How many males were there though? How many males should I have gotten? I should have gotten 18. Everybody's different. This is randomized. I should have got 18 is the true answer. I should have got 18, but I got 17. So a person who doesn't understand statistics will go, I got 17. You said I was going to get 18. You're wrong. I'm right. End of story. I hope from what you've learned in my course so far, you should be saying, wait a minute. You're telling me you told me it was 18. I got 17 is pretty close to 18. I don't have an argument against you at this point. You said it was 18. I got 17. That doesn't really seem like an argument. Now, keep adding the samples and keep adding samples until you can see that something magical happens. With all these samples, every single one of these dots represents a sample proportion. You took a sample of 30, you took a sample of 30, everybody takes samples of 30. So every single time, this is somebody selecting a sample of 30. If you keep adding samples, at some point you will notice something happens. What is happening to the dot plot? These are all random samples. If we keep adding, now you need to keep adding it as well. Yours, even though all of ours are all different, you should start seeing something that's happening. What is happening, people? Well, it's around, where is it centered? It's centered around 18. But what are you noticing about this as I keep adding? Now you can add more at a time. If I change add it to 10, it's going to add 10 dots at a time. Boom, it's added 10 more samples. 10, 10, 10, 10, 10, 10. What do you notice is happening as I keep adding more and more samples? I'm adding 10 at a time. What about something we've been learning about? What is happening to this graph? What is happening? This should start looking familiar to you. It's the normal model. If we keep taking more and more samples of all these sample proportions, it starts to take on the normal model shape. It's bell-shaped, it's centered. Now, where is the mean? Oh, on average, the mean is about 18. I should have got 18. It says, here's the mean that I got. Now, if I restart the simulation again, and I'm adding one at a time, and I keep adding. My hope was that at some point right around 80 or 100, you should start to, I would just go do it to 100. So if I reset the simulation, just reset it and do 100. So reset it and do 100 and then add the samples. Does that, for all intents and purposes, that looks, it's starting to look normal at 100. Does everybody understand that? This is a very, very big thing in statistics. This is what, and I'm going to call it, I'm going to write it down in your notes tomorrow. This is what is known as the central limit theorem. It is probably the most important theorem in all of statistics. The central limit theorem, in its most general sense, is saying the more samples we get, the sampling distribution will become more and more normal. So the bigger the sample that we get, and the sampling distribution will become more and more normal. And the standard deviation, and well, in this case, it's going to be, you're going to find out what that standard deviation is. Now, if I made a sample, in this case, I was sampling 30 at a time. My sample size was 30. If I took a sample size of 50, what's going to happen? If I took a sample size of 100, what was going to happen? That's what we're going to investigate tomorrow. We're going to add some notes in there. Now, here is the next thing. Okay, so let's say we took a sample of 30, and in my sample of 30, I got 15 people. I got 15 males. Is 15 unusually low? If you told me 30, if you told me 60% are male, and I took a sample of 30 and I got half, 15, were male, would you say that's unusually low? Is 15 unusually low? Yes or no? Yes, maybe. Let's find the answer to that. We're going to find the answer right now. So what I want you to do really quick, reset the simulation, put it at 100, and just do one sample of 100. Okay. So in the next screen, so what I need you to do is I need you to take a screenshot of this. To get your credit, you're going to take a screenshot of this, of yours. Take a screenshot. Huh? Control Shift window changer or commands on the window changer button. Command Shift window changer on the Chromebooks. You take your screenshot, you go back into here. On slide 12, what you're going to do is you're going to hit the plus right here. You're going to hit this plus right here in the left-hand corner. You're going to add an image, and then you'll find your picture, and you'll select done. It might take a little bit to load. Once you did it, you should maybe hit the plus or minus button. Hit the plus button probably once, and you'll have it right in here. And when you do that, I will be able to see your image. So see how Amanda, Mal, thank you very much. You see how I can see your image that you uploaded of your simulation. So this is how you upload images into Desmos. Thank you, those. Now looking at all everybody's images here, you should notice that, hey, they're all looking somewhat normal. So here's my next question. I just opened up slide 13. If you followed me, how many samples did you add? How do we answer that question? How many samples did I add? I added 100. You look at this number in the top right corner. That's how many samples you added. The next question says, what was the mean of my samples, of your samples? What is the mean? This number right here is the sample mean. Okay? What is the standard deviation? That is right there. And then comes the question, again, so what happens if what happens if in your sample you only got 15? So in your sample, what I want you to do is I want you to count up how many dots are below 15. How many dots are 15 and lower? So in my example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's pure coincidence that it was 15 out of the 15. I got 15 dots. Okay? 15 divided by 100. That's your answer for the percent. So my answer in my problem is I got 15 divided by 100 dots, which is equal to 0.15, so 15%. Is 15% unusually low? No. It is not. And this is what we're going to go into. Can anybody recall what percentage I said is unusually low? To be unusually low, it should be less than what? And I told you this way, way, way back early in the course, and I said, when we get to it, there's going to be a cutoff value. And I said, if anything, if the answer is less than this percentage, it's unusual. Does anybody remember that number? I know I said it really off the cuff a couple of times early in the school year. To be considered unusually low, to be considered unusual, the probability must be less than 5%. We got 15%. Is 15% lower than 5%? No. So the answer is it's not unusually low. Getting 15 is not unusually low. This is, as we will learn, this is called a p-value. It is something you're going to be finding. So what is my p-value? 0.15. Is that unusually low? Is that less than 0.05? No. Do I have evidence that whatever the hypothesis is wrong? No. If this number was less than 0.05, I do have evidence. I can make the argument, and I could stand up and say they are wrong. It is not 60%. I can't argue that it's not 60% based on this information. I do not have enough statistical data to say it is not. And of course, it really isn't. All right. I got to hide a couple screens. So what you just learned here, here is the actual formula for this. I'm going to put this in your notes tomorrow. I'm just going to run by this. So what should we expect as the mean? Whatever proportion P, which is 0.6, is what we should get as our mean. Our mean is 0.6. The standard deviation, here's the formula. I'm going to put this in the notes tomorrow. Basically, in this problem, let me unlock everything right now. We have some conditions that we're going to add, and I'm going to put these in tomorrow. Talk about sin as our mnemonic device. In this problem specifically, the mean would be 0.60, and the standard deviation would be 0.089. When I plug that math into my numbers, I'll show you tomorrow. However, if I look on the next screen, slide 17 really sums everything down. Basically, here's what we're trying to build towards in these next couple of 2 days. Here's me plugging into the formula. I get a mean of 0.6 and a standard deviation of 0.89. If I got 0.5, and this is what your homework is to finish this, what is the probability? What is the area underneath the normal curve? If this is the mean and this is the standard deviation, what is the area below 0.5? So if I got an answer of 0.5, what is the chance that I got something 0.5 or lower? That's what you're going to do, and you're going to tell me what you're going to type into your calculator to find that. So tell me what you got as an answer and what it would be. That's what I have for you today.